Hello everyone and welcome to this my video on resolution of a vector into rectangular components, part of the specialist maths course here in Australia, but vectors are universal all over the world. Hopefully this video is going to be useful. If you can do me a massive favour, hold on a moment. Who am I? I forgot that bit. I'm Darren from Maths Guru. Yes, my little corner of the interweb. If you can head over there and sign up, it's absolutely free and there's videos and downloadable lesson notes and so much more. And if you can subscribe and like this video on YouTube, that would be great. Nobody watches YouTube videos for maths content. And the fact you found this just says to me, hey dude, we're supporting you by subscribing. Makes life so much easier for me. Otherwise, I'm just talking to myself, really. Right, this is the second video dealing with vectors. And in the previous video, we looked at all the basics of vectors, right? And there was lots and lots in that video, if I remember rightly, particularly with the idea of linear dependence and independence. This becomes important. It comes up time and time again, right? When two or more vectors are linearly dependent, then one vector can be expressed as the sum of the other two vectors, which may or may not have been scaled, right? So what we're saying is, if I've got a vector here, he said, right? If I've got a vector going this way and a vector that way, then obviously by scaling them in some form, I can get a vector there. Okay, happy with that so far? All right, cool, lovely. It's going to build on the work from our previous video. Now, a unit vector, I have to say, for years, I had no idea. I would actually go into a freefall panic every time somebody said about vectors, particularly unit vectors, because I was like, I don't know what that means. And actually, it is so ridiculously simple, it's nuts. If we look at the idea here of a vector A that basically is 3, 4, it means I'm going 3 across that way. Oh, hello, and 4 up that way. Right, 3 units and 4 units. And there we go. There is my vector. A unit vector is basically a vector in the same direction as this, but only 1 unit in length. And I'd be like, okay, what do you mean 1 unit in length? Well, the first thing is, let's work out how long that is. Right? We can do that because we know we have Pythag. So if I do 3 squared plus 4 squared and square root it, that is going to give me that has there a length of 5 units. So a unit vector is effectively going to be 1/5 of that length there. Yes, 1/5. Why is it 1/5? Because we know that's 5. If we divide it by 5, we're going to get 1 unit long. And basically, we know that therefore the length of that is going to be 1/5 of my vector A. All right, so let's do that under there. So my unit vector, and we call it A with a hat, is equal to, well, not all of them are going to be a fifth, are they? How do we find that fifth? Well, we found the length of the vector. Oh, okay. Well, we know how to find the length of the vector because we've had that notation before. He says trying to do this. And there we go. Our unit vector, which is a vector that has 1 unit of length in the direction of any other vector, can be found by doing 1 on the modulus of that vector times that vector. There we go, and that is our unit vector notation. A hat is 1 over modulus of A times A. Now, ideally, that A should have a little squiggle underneath it, or I should have made it bold, but that's okay. Now, your CAS can make life so much easier for you if you know the notation that you are using, okay? And again, I've got the TI Inspire up there. Sorry, ClassPad users, my ClassPad isn't working at this moment in time, and so hopefully your notation is good as well. Now, first thing we do is we need to define or store our value of A, and there we go. We've got A becomes equal to Python notation and 2, 3, okay? And then to find my unit vector, I do unit VA. Let's see if my calculator will actually come up. Oh, it will. How exciting is that? So the first thing I'm going to do is I'm going to type, he says, using my calculator on the screenshot. I do that every single time. Let's close that down. Previous video, not interested. A, he says, type A and then control, and that button there becomes equal to, how am I going to put in, well, I'm going to hit that button again, and that one there, and I'm going to do 2 and 3, hit enter, and I always check that A was in there. It actually is. What am I going to do? Menu. Oh, look. Matrix and vectors. Oh, how do I do this? Vector. Oh, unit vector. There we go. Unit V of A. Hit enter. And lo and behold, out comes exactly we got on the screen there. But you're going to say 2 root 3, 2 root 13 on 13. How? Well, if we go back to the pencil and paper methods, we've got 2, 3. So we've got 2 going that way and 3 going that way. So there's 2 and there's 3. So we know that the mod of a in that situation is going to be the square root of 2 squared plus 3 squared, which is 4, and 9, which is 13, root 13. So we now know that my unit vector is going to be 1 on the square root of 13 times by, of 2, 3. Well, we don't really like that notation, but we'll give it a go. And so that's going to give me 2 lots on root 13 and 3 lots on root 13. And why is it different? They've just rationalized the denominator. Right, okay, unit vector. I, j, and k notation. Right, the unit vector in the positive direction of the x-axis is now denoted I. And then we got j, and we got k. Now, weirdly, and this always messes with my head if I'm brutally honest with you, is that although we have x normally and y, x, y, and z doing this way, well, we don't for vectors. For some inexplicable reasons, all right, we actually have x coming out, and then we got y going that way, and we got z going that way, all right? So just remember that in this situation, I tends to come out of the page, or out of the page as I'm looking at you, and then y and z, the other thing. But the point of it is that regardless of the notation, it still works in exactly the same way as we've had before. So for example, O to R could be xi plus yj, right? So that just basically means there's a point in space that we can use unit vectors to define about. And then if we have it in 3-dimensional space, it's I plus j plus k. All right, cool. Adding and subtracting an ijk notation is really easy. If we have a vector, let's say A is equal to I plus 2j plus 3k, and we have B is given by I minus j plus 4k. All right, if I want to do A plus B, for example, I simply add the i's, the j's, and the k's terms together. So I plus I would give me 2i, 2j minus j gives me j, and 3 plus 4 would give me 7. So in exactly the same as it works in 2-dimensional space, it works in 3-dimensional space as well. Right, let's look at some basic examples, and wow, these are basic. Right, what do we got? O2a is going to be, well, it's telling us that one unit there is I, so it's 2i plus 3j. And hopefully I've not got this wrong. Good. So that's 2i plus 3j. What's O to B? Would be 1, 2, 3, 4i plus j. O to C would be I minus 2j. And then O to D would be minus 1, 2, and up 3. So minus 2i plus 3j. Whew, did I get those right? I did. World's gone crazy. Right. Using the vectors I and j, give the vectors A to B. Well, A to B is going to be minus 2i. Oh, no, it's not. Try that one again. It's going to be 2i minus 2j. And what about the next one? B to C. B to C. I'm going to go from B. So I'm going to go down 3 and back. How many? 3. So minus 3i. And minus 3j. Okay, what about the next one? Find the magnitude of the vectors A to B. Right, so I'm just going to draw a beautiful line on that one. Is it going to work? It is. I'm going to do that one. So I've got minus 2, and I've got 2. So therefore, the magnitude of AB is going to be the square root of minus 2 all squared plus 2 all squared. And then 4 plus 4 is going to be root 8. And there we go, which we know is 2 root 2. All right, what about that one? B to C. B to C. Let's draw that on a different way. Ka-ching. We got that one, we got that one. So what is that? Minus 3 and minus 3 again. So the magnitude of BC, is equal to the square root of minus 3 squared plus minus 3 squared, which gives me 9, plus 9, which is 18, the square root of 18, or 3 root 2 as my answer. Did I say this was complicated? Not really. Now, again, your calculator can do a lot of the hard work for you, and I tend to find in later sections of the video or this course, my calculator does all the heavy lifting for me. So again, we've got A is defined here as I plus 2j minus k. Now, on my calculator, I can simply define that as the numbers. I don't need the I, J's, and K's. Your calculator seems to be clever enough to work that out. So there I've defined A as 1, 2, minus 1, simply because we've got 1, 2, and minus 1. B, I've got as 3, 0, minus 2. The reason is there's no J term. And C would be 2, 1, 1. There we go. And basically, once I've done that, your calculator's clever enough to know what to do next. So if I've got A plus B, it gives me 4i. So there we go. We're going to get 4i plus 2j minus 3k. And again, we could have done that by just reading. But A plus B has got the I term plus the I term. Where is it? I plus B. So I plus 3i is my 4i. I've got a 2j, but I don't have a j term in there, so it's just 2j. I've got a minus k minus another 2k's, which gives me minus 3k. A minus 2b, again, put it into my calculator, gave me minus 5i plus 2j plus 3k. And then A plus B plus C is 6, 3 minus 2, which is 6i plus 3j minus 2k. The CAS is doing all the hard work. Now, this one here, the modulus of A is not a case of putting it into calculator. Although I say that, I'm actually going to try something now on my calculator because I'm never really sure whether it's going to work, all right? Because if you look on the screenshot here, to find the modulus, you type norm. It's the norm function, which I never remember. Give it, 2 minutes. But I noticed on here, I have that function there. So let's do that. And I'm just going to do A and see what it does. And actually, no, it doesn't do anything there. So in that situation, although the notation looks like the same as the TI Inspire calculator, don't do that. You have to go menu, vector, norms, norm, and then A, and hit A, and it gives you root 13, right? So that is the length of A in that situation. He said, stupidly not bringing up my calculator. So let's just talk about that one again. If I do the control and that key, no, try that one. If I do that one, you'll notice I get this, modulus on either side of it, but that doesn't actually work, all right? As I can demonstrate here, when I did that with my vector A, it just basically gave me back my vector A. I had to go norm, which again was menu, matrix, norms, and norm. And lo and behold, out came the value it did. Next time, Darren, remember to turn on your calculator. All right, so there we go. More 3D type of questions. A cuboid is labeled as shown. O to A is 3i. Now, whenever I get this here, I tend to always put on O to A is 3i. And you notice I comes out of the page. O to B is 5j. That's 5. Oop, he says right now again. 5j. And O to C is 4k. Now, the arrows are really, really important because if you don't get those right, you're going to mess up. Right in terms of I, J, and K, D to B. Well, D to B is basically the same direction as O to A, the same vector as O to A, but in a different direction. So I'm going to write there that is going to give me minus 3i. What's the next one? O to D. O to D, to go from O to D, I need to go here, and then here, or here, and here. So probably going to do that one, 3i plus 5j. So we're going to say 3i plus 5j for that one there. D to F. Oh, bit my tongue again. D to F. I can go along here, up here, and along here. Oh, no, that doesn't work. Well, maybe we'll do that one there. Oh, happens to be the same length and in the same direction as O to C. So that's just going to be 4k. And what have we got here? O to F. O to F. Well, O to F is O to A to D, and D to F. That's one way, and there are lots of different ways of doing it, but I'm going to go O to A to D, and D to F. So OF is equal to 3i plus 5j plus 4k. Right? Find the magnitude of O to F. Now, in exactly the same way as it works in two dimensions, to find the magnitude there, you'd literally take each of the I, J, and K terms, square them, add them together, which is going to give me 9 plus 25 plus 16. And I'm going to square root all of that, which is basically the root of 50. And that gives me 5 root 2 as my correct answer. If M is the midpoint of FG, find O to M. Well, F to G is going to be minus 3i, but that doesn't help me, does it? So F, what am I trying to find? O to M. So O to M is equal to O to A plus A to D plus D to F plus F to M. All right? Happy with that so far? You put all the little arrows over it. That makes life easier. Right, O to A is 3I plus A to D is 5J plus D to F is 4K. We're happy with that so far. Plus F to M. Well, F to M is a half of F to G, which is 3I plus 5J plus 4K. And that's a half of F to G is the same as minus 3I. So 3I minus a half of 3I is going to give me 3 on 2I plus 5J plus 4K. Now notice how we did that. There may well have been lots of other ways to be able to do this. I could have done O to F plus F to D, or half of F to G. Anyway, I'm making no sense. The modulus of that length, well, if I wanted the mod of OM, I'd basically square root each of the, square them, add them together and square root. And apparently it comes out as a half root 173. Oh, loving this. Now, let B equals find M, the midpoint of AB. Now, interestingly, I've said here, hint, always draw a diagram. At the moment, I know how to find the midpoint between 2 points, because all you do is you add the X values together, divide by 2, the Y values, divide by 2, the Z values, or in this situation, the A values, the I, J, and K values. And so the midpoint is going to be equal to 2 plus 5 on 2, comma, minus 4 plus 1 on 2, comma, 5 plus 7 on 2, which is going to give me 2 plus 5 is 7, so that's 3 on 2. Minus 4 plus 1 is minus 3 on 2. And then what have I got here? 5 plus 7, 7, 8, 9, 10, 11, 12, comma 6. And there we go. I think the midpoint is going to be given as that, basically. Now I moved on and it's gone, oh, well, actually you could do this geometrically. And I'm like, well, you could, but why would you want to? All right. So the point of it is here, you could say, you could try and find out what A to B is. And AB is basically A to O plus O to B. Right, so A to O is the opposite of that one there. So it's basically minus 2I plus 4J minus 5K plus O to B is going to be 5I plus J plus 7K. Now when we do that, we get minus 2 plus 5 is 3I. 4 plus 1 is 5. 5J and minus 5 plus 7 gives me, minus 5 plus 7 gives me 2 plus 2K. There we go. So that's AB. So we now know A to M, which is a half of AB, is basically going to be then 3 on 2I plus 5 on 2J plus K. All right, so that's A to M. All right, so we now know that O to M is equal to, O to M is O to A plus A to M. Well, O to A is 2I minus 4J plus 5K plus A to M, which is plus 3 on 2I plus 5 on 2J plus K. Well, that's going to give me 4, 5, 6, 7 on 2I. Minus 4 plus 2.5 is minus 4 plus minus 1.5, which is 3 on 2J plus 6K. Now, I don't know about you, but I know which one I think I preferred. Yes, but no, not that one. All right. Our old friend, linear dependence and independence. Right, example, show that the vectors A, B, and C are linearly dependent. For that to be able to happen, there would have to be one solution to the idea that we could take some fraction of this one, where are you, B, and some fraction of that one. And when you take them and add them together, you will in fact get that value there. So writing it out as we would have done before, you would have had 8, 7, 3 is equal to m lots of 1 minus 1, 3 plus n lots of 2, 3 minus 1. Now, when you write those out longhand, you get 8 is equal to m plus 2n. You get 7 is equal to minus m plus 3n. And you get 3 is equal to 3m, not plus, minus n. And when you do that, and you'll notice that those are the equations I've got here. So 8 is equal to m plus 2n. 7 is equal to minus m plus 3n. And whatever else. And you put those into your calculators and solve for m and n, you do in fact get m equals 2 and n equals 3. And if that's the case, they are linearly dependent. You can do exactly the same with the next one as well. All right, so that works just as well. The final part of this video, really you just have to take as gospel. If you want to, there are sections in the book that I believe explain that to you, but it's way, way, way beyond what I'm going to do at this moment in time. But we can find the direction a vector can make, all right, with the I, j, and k directions using these formulas here. So the cosine of alpha, assuming alpha is the angle made with the I, beta is the angle with the j, and gamma is the angle with the k. We can use these formulas here, okay? Now, how do we use this here? If we let A equals that, and B equals that, for each of these vectors, find its magnitude and the angle the vector makes with its y-axis. All right, angle it makes with the y-axis. So we know the magnitude of A is given by the square root of 2 squared plus minus 1 all squared. That's going to be 4 plus 1, which is 5, which is going to be root 5. And the magnitude of B, therefore, is going to be equal to the square root of 1 squared plus 4 squared plus minus 3 squared, which is going to be 1 plus 16 plus 9, which gives me the square root. What does that give me? 16, 17, 26. Root 26. All right, so the magnitude the vector makes with the y-axis. Now, if we go back to my y-axis, that's the cosine of beta is equal to a2 on the mod of a. What on earth is this a2? Well, again, if it's with the y-axis, we actually need the whatever's in front of the j term to be able to do it. Okay, right, so if we go there. So let's do the first one first, where we've got a. So the cosine of, let's call it beta, is equal to whatever's in front of the j term, which is minus 1, divided by its modulus of root 5, which when we put that into the calculator is roughly 116.57 degrees. Okay, now again, it didn't say to do it in degrees, but it makes sense to be able to do it because you're looking for an angle. What about the next one for B? So the cosine of beta for that one there is whatever's in front of the j term, which is 4, divided by its modulus of root 26, which when I work that out gives you beta is approximately 38.33 degrees. Okay, so that's the basic fundamentals. A position vector in 2 dimensions has a magnitude of 5. Ooh, magnitude of 5. So we know from that automatically the mod of A is equal to 5. And its direction measured anti-clockwise from the x-axis is 150 degrees. Okay. Now, drawing this diagram makes life a little bit easier because what we know is that that now is 150 degrees and from the y-axis it's 60 degrees. How does that help us? Well, we now know that we can use the formulas from before to help us be able to work out our values because we know that the cosine of alpha, which is the angle from the y-axis, is the I, which we don't know, so we'll call that A1. Divided by its modulus, which in this situation is 5. But what was alpha? Well, from the x-axis, we know it's 150 degrees. Okay, so that's 150 degrees. So A1 is equal to 5 times the cosine of 150 degrees. And we know the cosine of beta, which is from the y-axis, is going to be equal to A2 on the modulus, which is 5. Well, we know what beta is again. We know that beta in this situation is 60 degrees because we know the angle from the y-axis is 60 degrees. So A2 is going to be 5 times the cosine of 60 degrees. And so therefore we can say that A is going to be equal to, well, putting this in is going to be minus 5 root 3 on 2i plus 5 on 2j. Where did I get those values from? Well, again, this is my A1, which I just solved here. This is my A2, which I solved there. And life becomes easier. Wow, that lesson went really quickly, did it? How long did that take? 25 minutes, maybe not that quick. Thanks very much for watching. Hopefully it's been useful. Again, these are the building blocks that we will use as we go through the videos. They are on their way on mathsguru.com. I may have mentioned that. And if you can like this video and subscribe to my YouTube channel, it just tells me that, hey, I watched. Thanks very much, dude. Take care. Hopefully I'll see you again. Stay safe. Bye-bye.